Now that we've developed some vocabulary and understanding of vectors in n-dimensional space as a generalization to what we saw in Calc 3 in 2 and 3-dimensional space, we want to now use these to try and understand more complicated things, right? That's kind of, zoom out, look at the big picture. A lot of the methods and the progression of mathematics has started with something simple, and then, okay, we know something simple. What can we do to understand something less simple or less trivial, right? So we'll start with understanding, we started with, okay, what's a number? And then what's a point? And then, okay, what's a vector? How do we use vectors to understand the world around us, right? And, parametric lines isn't something super relevant in everyday life, but it's something that's an application of understanding vectors. So let's start with remembering kind of in general. Let's have a little bit of review here. So remember, if you have, let's look in R2. If you have a function y equals f of x here, this is an equation in, we'll call them Cartesian. They're sometimes referred to as rectangular. Cartesian coordinates. The Cartesian here basically means spatial, right? So we're looking at this function y equals f of x, and the function f, what it does is to every point x, it assigns a value y, right? That's what a function does. And so here would be x, here would be f of, well, let's say if this is x naught, that would be f of x naught, right? And for a collection or a family of points x, you get a curve, say something like this. And so we know that the geometric interpretation of an equality here, right? Like this algebraic expression, y equals f of x, these are in one-to-one correspondence with curves or graphs in R2, right? And basically what this is, or what we have here, is we have for every function y equals f of x, this is denoting a one-dimensional subspace of two-dimensional space, right? Or if you have taken Calc 3, and let's say we're looking in R3, and then you have something like z equals f of xy. This is in Cartesian or rectangular coordinates again here. And what this is representing, like this algebraic statement, for each of these statements, it's a one-to-one correspondence with surfaces in R3, right? And so we had here that this was representing a one-dimensional curve in two-dimensional space. Here we have that this is representing a two-dimensional, we don't call them curves, we call them surfaces, right? In three-dimensional space. And functions, kind of how they work is they're describing a set of points in as a subspace of the kind of ambient, if you will, the ambient space that you're working in. So, if you were looking at R4 here, we would have, let's say maybe W equals f of x, y, z. This is representing a 3D, what we call a hypersurface in 4D space. And this generalizes to in dimensions, right? And so the function, so in Rn, if you have, say, xn is a function of x1 through xn minus 1, right? What would this be? This would be representing an n minus 1 dimensional hypersurface in n-dimensional space. Right? And so we really care a lot about like these subsets of space. But to understand these more complicated subsets of an n-dimensional space, we have to build. Again, we have to start with something simple. And so what we're going to start with is looking at just lines, right? We're going to look at specifically one-dimensional lines in n-dimensional, let's say. I avoid this notation because it looks kind of weird, but in ND space. Okay, so how do we understand lines? Well, again, to look at the big picture, there are many ways we can understand the same curve or the same surface or whatever, right? If you've taken Calc 3, you can understand a function. So like for R2, we can understand the same function, y equals f of x. Well, we could understand it in like it being parameterized. So you would have like x of t, y of t. We can understand it in polar coordinates, say like r is a function of theta, right? And there are other coordinate systems. These are the main ways we understand curves in R2. And we know in R3, let's just kind of use this space down here. In R3, for z equals f of xy for some surface, well, we can still understand this in parametric equations. By parametric, I mean you introduce time, and so everything is kind of viewed as in a time variable. We can understand surfaces in cylindrical. We can understand them in spherical coordinates. We can understand them in more complicated things like toric coordinates. Toric coordinates would be if you were to map out, or it would be the most convenient coordinate system for understanding a torus, which is like a donut, right? If this was living in 3D space here. And so there are many different ways that we can understand the same surface or the same object. And it's important that we understand how to understand them in as many through as many lenses as possible, because depending on the setting, one may be more advantageous or more simple than the other. And so for lines, usually parametric is kind of the nicest approach, because the behavior of a line is pretty tame, right? It's linear, there's no curve, the derivative is constant. We know quite a lot about lines, and maybe one of the easiest ways to think about a line is to think about a line extended from a path between 2 points, right? And so let's say we're starting, let's imagine this was a deleted verse from John Lennon's Imagine, by the way. So let's imagine that we have a particle traveling along a line, let's say L, and this is going to be in n-dimensional space. So that wasn't very good. Let's call this line L, and this will be a subset of n-dimensional Euclidean space. We'll call this line L, traveling along a line L, starting at point P and ending at point Q, right? So we have some particle, or maybe a person, and you're traveling from P to Q. So if you'd like a kind of a better example here, let's say P is yard bar in Aggieville, and Q is what's right there. Say Q is Jimmy John's is right there across the street. You know, and after all your shots at yard bar, you would want to travel straight to Jimmy John's. And so we want to figure out the equation of your path from yard bar to Jimmy John's. And how can we do this? Well, luckily we can do this, find this equation only using information about the starting and ending point. And so here's kind of a remark. Well, let's have two remarks here. A line L is uniquely determined by 2 points. Let's say P and Q that are in Rn, right? And so the picture here is in R2, but this generalizes quite nicely. Let's imagine we're in 3D space and you have 2 points. A line between these 2 points is still unique, right? Even with the extra degree of freedom in the third dimension, you can't construct a line only passing through these 2 points. Certainly if you could have something, you could have a one-dimensional subset, right? You could have a parabola, you know, there's probably an infinite number of curves passing through these 2 points, but a line is still uniquely determined by these 2 points. And that's true in Rn, right? And so because these are uniquely determined by 2 points in space, that's all of the information you need. So let's say P is the point P1 through Pn, and Q is the point Q1 through Qn here, right? And so we have L contains points P and Q. So this backwards epsilon here, you know, this means is in or is an element of. Well, if you reflect that about the y-axis, you get a backwards epsilon, and this means contains, right? So it's just changing the order of your statement. But anyway, let's find an equation for this line L. Let's look at this in a parametric. Let's look at this through a parametric lens here. So let's say we're at P at time t equals 0 and Q at time t equals 1, right? And so we can we could scale our time, or how we're subdividing our units of time, so that traveling from P to Q takes exactly 1 unit, right? Well, then how could we find an equation for this line? Well, how do you find an equation for a line in R2? And let's look at Cartesian. Usually what you do is you first you locate a y-intercept, and this is kind of like a home base or a starting point, right? So this would be like a y-intercept. And then we also need the slope, which we'll call m. Then how do we describe this line? Well, we describe this line based on the slope and the y-intercept. And so we have, you know, our generic formula for a line, y equals mx plus b. And so to find an equation for a line in n-dimensional space, we need a parallel of slope. And so slope kind of turns into a direction vector, right? This line, L, has some direction to it. And we can find this direction vector by finding the vector between P and Q, right? That certainly lies along the line L. And so what we're looking at here to generalize, so here's our equation for the line. This is going to be the direction vector times T, because we're in parametric equations here, and then plus B, our y-intercept. Again, we kind of think about this as like a home base or a starting point. And so if we're traveling from P, remember I have starting at P and ending at Q, well, we can think about P as being the home base, right? Or where we're starting. And so what we need here is we need a vector that describes where we're at the point P, right? Well, if you'll remember, we have a position vector let's call it P naught, which means if P is P1 through Pn, then the position vector P naught is the vector P1 through Pn. And this is really kind of our starting point. And so let's say this is our starting point. Or it's the vector at T equals 0, right? Because at time 0, that's where we're starting. So let's be more explicit about what this is. Well, we learned or have deduced that the direction vector is the vector PQ times T plus P naught here. And so this describes a line between P and Q. And all you have to understand, or all you have to know, is P1 through Pn and Q1 through Qn, right? If you know those values, if you know the coordinates, then you also know the equation of the line starting at P and ending at Q. Some vocabulary here, we call this the vector form of the line L. We can be more explicit, right? Because we know what PQ is. PQ is going to be Q1 minus P1, Qn minus Pn, and we already know what P naught is, right? It's P1 through Pn. Well, then we can be more explicit about the description of our line L, right? This would be the direction vector Q1 minus P1 through Qn minus Pn times T plus P1 through Pn. We can be more explicit because we know how to multiply a vector by a scalar, and we also know how to add two vectors. So this would then become Q1 minus P1 times T plus P1, et cetera, Qn minus Pn times T plus Pn. Now, what do we have here, right? And so we've written this much more explicitly, and we'll call this our component form, right? Because we're now much more explicit with the components of this line here, right? More commonly, and so maybe let me say here, this is like pre-component form or like pseudo component form, because normally how we see component form is if you have a vector v, you know, it's given by x1 through xn, right? And so the first component is describing the behavior of the vector in the first variable, right? And so truly what component form is you set x1, your variable x1, equal to the component for x1 in the vector equation here. So we would have q1 minus p1 t plus p1 all the way down to xn equals qn minus pn t plus pn. And so this is really truly what component form is. And it makes sense, right? Because we have an equation for each component here. And again, since this is a parametric equation, we need to describe, or we need to give a domain for our time here. This is for the line segment between P and Q, or I should say from P to Q, right? For the line, kind of, the extension of the line segment, well, then you would let T vary infinitely, right? So from 0 to 1, you've described this line segment. And then if you let T kind of expand from negative infinity to infinity, then you get that entire line. Okay, so let's do an example here. I think examples are just as important as theory, right? I mean, to truly master something, you have to be good at the theory and the practice or the application, right? And so let's look at an example in R3. Let's express the line L containing P equals 1, 2, 0, and Q equals 2, negative 4, 6 in component form. Okay, so what do? Well, we start at P, which means we have a position vector P naught given by 1, 2, 0, because the point P is 1, 2, 0. And then we have a direction vector PQ, which is given by 2 minus 1, negative 4 minus 2, and 6 minus 0, which gives us the vector 1, negative 6, 6, right? And then let's look at what the vector form of L is, right? Then this is PQ, which is 1, negative 6, 6, T plus 1, 2, 0. So here, this would be our vector form, right? But it asks for component form. What does this simplify to, right? Because basically, to get component form, you're just simplifying vector form and then assigning to each variable the respective component, right? So this would be the first component here is going to be 1 plus t, right? And so we have L is given by 1 plus t, and then 2 minus 6t and 6t. So component form would be x equals 1 plus t, y equals 2 minus 6t, and z equals 6t. And so this would be your answer. And again, to be very thorough, this is t between negative infinity and infinity. Great. So that was a good example. One thing you may notice, or something you can observe, is that when you're in component form, these are all linear functions in t, and so that means you can explicitly solve for t in every equation. So if we rewrote this component form to where we solve for t in each equation, well, the top equation would say t is equal to x minus 1, y is equal to, t would be equal to y minus 2 over negative 6, and t would also be equal to z over 6, right? Well, by the transitivity of equality, we could get a chain of inequalities. It says x minus 1 equals y minus 2 over -6 equals z over 6. So the points x, y, z that satisfy this chain of equalities here also describes the line L. And we call this the symmetric form. And this has benefits because it is invariant of time. In certain settings, time can be too restrictive or you don't care about time. You just care about the spatial position here. And so symmetric form is a good form when you don't care about time, or if you need to kind of understand this line intrinsic of time, right? And so let's look at symmetric form in general. Right? And so if we have a line L that we learned was given by x1 equals q1 minus p1t plus p1 all the way down to xn equals qn minus pnt plus pn, right? Well, if we solve each of these for t, what we would get, well, what would we get in the first one? We would get x1 minus p1 over q1 minus p1. For the second one, we'd get x2 minus p2 over q2 minus p2, et cetera, xn minus pn over qn minus pn. And so here is your symmetric form in an arbitrary dimension, right? Cool. So that's where I'll stop for parametric lines. And what we'll do now is start to look at, we've talked about scalar multiplication of vectors, but we haven't talked about the multiplication of a vector times a vector, right? And so I think a natural question is, great, we can multiply a number times a vector, but what about the product of two vectors? And it turns out that there are many notions of the product of two vectors. We'll explore 3 of them in this class. We'll look at the dot product in the next video, and then later we'll look at the cross product and then the box product. And we'll see what is happening when you take these different products of two vectors.